I'm primarily a theorist, and so anytime a theorist comes in front of a group of astronomers, particularly amateur astronomers, they know the sky way better than what I know.
The annihilation stuff.
But today I want to talk with you about some topics of planet formation. And the way I would like to approach it is I want to talk a little bit about what we can call traditional planet formation. And that is kind of some of the ideas up until the past decade. And then I want to talk about how the discoveries of planets outside of the solar system have continued to shape our understanding of the formation of planets, and also have really changed radically some of our ideas. And you know, with only 4 hours to give this talk, I don't know how I'm going to fit it in, but I'll try. All right. The first place I want to start is right here with Tycho Brahe. And the reason I want to start there is there are two reasons. One, really our understanding of planet formation came from understanding planetary motion. And that's really what ended up driving some of the very first stages of understanding the dynamics of planets and how they could come to be. But these were observations. Those observations led to very detailed calculations and models based on those observations. And those are now known, those detailed models became Kepler's laws. So mathematical relations based on these models of, at the time, absolutely exquisite data. And then, based on, largely on this work, as well as other work, then Newton was able to refine that and really bring to the forefront of science then the prediction cycle of science and very modern theory as we have it. So all of this was observationally driven. From the start, planet formation has been observationally driven. It all goes back to Tycho. And it's not any different today. So I'd just like to keep that a little bit in mind. One thing to keep in mind is certainly we have a lot of information about the solar system today. But that information is also rather biased. We're trying to do our best to take ourselves out of the solar system and look at planet formation more holistically. But most of our ideas are going to be heavily based on the solar system. We're going to see that take shape throughout this 4-hour talk. So the distances here are not given to scale, but the relative sizes are. Just to keep that in mind, because we're going to be coming to that again. Another thing that gets me very excited about planetary science is that we're at a stage in which science fiction truly has come to life. I can go in front of you and tell you a very interesting fact that we now have, our species has a spacecraft that is in interstellar space. Not interplanetary space, interstellar space. It's leaving the solar system. But it has, for all intents and purposes, left the solar system as defined by how the extragalactic particles the galactic particles mix in with the solar wind, the particles that are launched by the sun itself. And so we now have Voyager 1 that is leaving the solar system. There's still an influence of the solar system here called the Oort cloud, a giant cloud of comets that extends many, many times the Earth-Sun distance. This is a log scale. So right here is Earth at 1 AU. 1 AU is 1 times the distance between the Earth and the Sun. To Saturn, about 10. We go out to Voyager 1, a little more than 100. We go out then to the edge of the Oort cloud, 1,000 times the distance between the Earth and the Sun. Go out to the edge of the Oort cloud, hundreds of thousands, and you go out to nearby stars, and we're talking about millions of times the distance between the Earth and the Sun. But we now have a spacecraft that is in interstellar space. This spacecraft, Voyager 1, has given us amazing photos, and it also has something amazing on it as well. How many of you know of the Golden Record? So how many of you don't know of the Golden Record? That's okay, that's okay. There's so much stuff to know. So this is a record, and on this is an attempt by our species to communicate with any other species that might actually find us. This tells, hopefully, someone how to build an apparatus, a record player, to actually read the data. And when they do that, it will play sounds, greetings from Earth, sounds of animals. It will show pictures if they can decode those pictures. And so this is a record our species has that has left the solar system. I think that's kind of cool. Of course, we don't have to go very far away to actually be doing some amazing things in planetary science. I mean, we have an SUV on Mars. Yeah, this thing, that's an SUV. And it has a laser beam. So some of the instruments are able to vaporize a little bit of rock, and then it has a spectrometer that's able to then take a look at what is actually the chemical composition of that material to help us analyze it. But I like to think of it as a giant robotic SUV on Mars with a laser beam. So I encourage you to think of it likewise. And this actual rover, along with the other rovers, don't worry about all this junk here, but have given us some amazing views from the planet Mars. And this is a particular view in the Yellowknife Bay Formation. And this area was probably a lake. And the material here is full of mudstone. And so there's probably, this is, as we analyze Mars, it does look like Mars was once a very wet place. And as we analyze it more and more, we see that there is both extinct and possibly extant glacier movement on Mars that's creating a lot of the structures that we see. And so there's both, the planet is being shaped by certainly water, ice, and in the past perhaps even by water. Then, why stop at a planet? You can go out to a comet. And then once you're near that comet, if you want to analyze the interior of the comet, you just send a projectile to it and slam into that comet. This is Temple 1. This is the deep impact. This is now a decade old or so. But actually sent an impactor from a space probe, and it intercepted the comet, collided with it, sprayed a whole bunch of material from the comet, and then the spacecraft was able to analyze it. And so actually this is something that's happened, and it's a stepping stone to some of the ideas that are being thrown around about how to further study the solar system, such as actually bringing asteroids to us. What can go wrong?
Is that picture on the right, is that a real photograph?
So this is an actual image from this. So it had a spacecraft, and in that probe then was another probe that was launched and it impacted. And this is taken from the actual spacecraft, and that's the probe. And there's actually, you can go on NASA's website and see the probe on its way in. Boom. After the main probe actually went by that comet, it continued on its way in the outer solar system, in the solar system, not too far out in the solar system, but it went by. Then Hartley 2. This is another comet. This is somewhere around 1 kilometer or so, times a factor of order unity. And then here are some jets that are coming out of that comet. So we're seeing some unprecedented detail here with actual bodies in the solar system, sending probes right by them, actually impacting the probes, and landing on these, probes, the bodies, actually be landing on them soon. New Horizons. This is on its way to Pluto, and then into the outermost parts of the solar system, the icy bodies that are far beyond Neptune. This is one of the last images New Horizons took before it went into hibernation on its long way to Pluto. And this is Jupiter, and that's Europa. Europa is a moon around Jupiter. Europa probably has, even though it's a moon, probably has more water than the Earth. At least in the Earth's surface of Earth's known hydrosphere. This has about twice the amount of water.
Is it frozen?
So it has it's an ocean. And it has a layer of ice, and then beneath that ice is then most likely a 100-kilometer thick ocean that's in contact with ground. And there's another moon, Ganymede. That moon has that also has an ocean, we think. But it's big enough that it actually has enough pressure that it converts the ocean back into ice as you get closer to the surface. And as a result, then that ice, the ocean is no longer in contact with any ground. The reason why that's important is because if you have lots of stretching of a moon due to tides, like around Jupiter, that can actually keep a moon volcanically active. Io, which is one moon closer into Jupiter, is the most volcanically active system known in the solar system. It's turning itself inside out because it is just tidally heated by, it's tidally heated. So it's not going to be as intense on Europa, but it's still there. And then if you have water then in contact with then thermal vents and an ocean floor, that's interesting. That's interesting because if you could then have a very oxidized water come down to a very reduced environment, then you could have chemical disequilibrium, which is a way of getting energy ultimately. And then you have a medium for organic chemistry, you have a power source, and you have a food source. It's of astrobiology interest. Yes.
How do they know there's granite in the center of the...
So you can look, for example, you can look at the way the moon behaves on its orbit. The orbit is a little bit elliptical, which is ultimately what gives it its behavior as it moves. Is one component that gives you a little bit of information about its moment of inertia. And then also, if you take a look at the way a probe orbits it as it goes by, then that also tells you something about the shape of the moon. It ultimately tells you about the shape of the moon and the way it's being deformed by both Jupiter and its response along its orbit to other perturbations. All that information actually tells you a lot about its interior, and so you can use that, for example. And so that's that. And also then just models. If it does have liquid water as an ocean, then it won't reach the pressure that would be needed to convert it into ice. It's well out of that regime. So either the whole thing is going to be kind of this warm convective ice all the way down, or it's going to be actually water. And now there's actually observations of it spraying water, so it actually helps. Now, this is new, just a week or so. It was the case that there are 4 bodies in the solar system that had moons. Those are the giant rings that had rings, and those are the giant planets. Now there's a 5th object. The giant planets and this little dinky 100-kilometer thing. This is a centaur. It's a leftover piece of the formation of the solar system. It's icy, and it's between the orbits of Jupiter and Neptune, and so it's getting dynamically kicked around, and it's not going to be around very long. But this is one of the bigger ones, and what they were doing is a stellar occultation observation. They were just waiting for, then, from our point of view, the object passing in front of a star. And they were going to just watch the light dip. They would do that from different positions because they wanted to get the shape of this object. Well, when they did that, they saw this. Blip. Blip. That's a ring. Very, very clearly, that's a ring from stellar occultation. In fact, that is exactly how Uranus's rings were discovered. The exact same way, stellar occultation, trying to get the size of the object. And so this is hot off the press, and there's still so much we're learning. We have probes now that are leaving the solar system, and we are still learning some basic components of the solar system itself. As we go farther out, there are objects that are now seen at great distances from the sun. And this doesn't tell you its average orbital distance from the sun, the semi-major axis, but it's telling you its perihelion distance, its closest approach to the sun. So these are objects that have a closest approach that is around 80 times the distance between the Earth and the sun. And so we're now finding at least two of these objects that are around the closest approach of only 80 AU, and probably more out there. So we're still trying to put together the inventory of the solar system. So this is our biased view. But it's what we have to work with. So let's go ahead and think about some things that we see here. All right, so we have little dinky things up here close to the sun. These are rocky objects. As we go away from the little dinky things, we get a huge jump in size. So this is 11 times the size of Earth, about 320 times its mass. And then it slowly trails off in mass and size. Actually, Neptune is a little bit more massive than Uranus. So that's, I'll try to get to that later in this 4-hour talk. Okay. So one thing that is illustrative here, it's not meant to actually show it, but the artist has put everything in a plane. And that's when we go out, we actually do see that the planets are more or less in the same plane, a few degrees here and there. Well, what's a few degrees between friends? That's a plane. So why are they in a plane? Well, if we want to talk about planet formation, we need to talk a little bit about star formation. To the best of our knowledge, planets only form around stars. And so if we want to understand the very first stages of planet formation, we have to know a little bit about the star formation process itself. This is the Eagle Nebula. I'm sure many of you are aware of that. And in here are perhaps stellar nurseries, little concentrations of gas that are denser than the surrounding material. And in there, new stars are forming, or perhaps will be born. Let's go ahead and cartoonify it. So in the upper left, that's my attempt at putting down a dark cloud. We just have some dense gas that's much denser than the rest of the material around it. This is going to be both dust and molecular gas. By molecular, just think very cold at this point. Something happens, and we transition to a point of gravitational collapse. As for some reason, gravity is able to overwhelm that dark cloud's support, and it starts to collapse. Now, if it has any wee bit of rotation, just from random motions, you have a whole bunch of these clouds, and each one of these clouds will have some random motion in some way that is maybe a slow rotation. As it collapses, it will spin up, just as an ice skater will, due to the conservation of angular momentum. And that will allow the central regions, which do not have a lot of rotational support, to simply collapse. And the material that's coming in this way will eventually become rotationally supported. it will go into orbit. And so you get a disk. This part just collapses. This part collapses until it goes to orbit, more or less. A little bit of a pressure support here, and we'll talk about that. But this is a basic picture. And the reason why you get such spin up and you're able to actually make the disk and prevent that material from falling in is because you're going from size scales of hundreds of thousands of AU, hundreds of thousands of the Earth-Sun distance, to hundreds of AU. And that's, so even just a little bit of rotation initially goes a long way, and eventually you become rotationally supported. Let's talk about little pieces of evidence for those 3 blocks that I have. So this is a Bach globule. This is some dark hole in the sky. So it's a dark cloud. It's blocking a lot of stars. Now, some people went and looked at this at a whole bunch of different wavelengths. And what they were able to do then is measure the amount of stuff that was in front of the star by looking at the different wavelengths. It's an extinction. And what they were able to do with that is then turn that into a density, a gas density, versus distance from the center of that core. And if you do that, then you could compare that with some of our ideas of what these clouds should look like. And this is the theoretical model that was predicted well before this observation. And here are the data. Well, that's pretty good. This is the best observational evidence we have of one of these objects being an actual, the theoretical object is the Bonner-Ebert sphere. And so this is a gas cloud that's more or less in equilibrium. And so we think that this is at least a candidate for star formation. But something still needs to happen to cause that to actually collapse. Either there's a little bit of support from this from maybe some magnetic fields. And maybe the magnetic fields need to diffuse out to some processes where they decouple from all the atoms that are in here in the molecules. And maybe that would allow it to collapse. Or maybe there's winds from nearby stars that are causing extra compression that eventually overwhelm it and it collapses. Or maybe a star nearby will go supernova and that will cause a shock, that will cause material to ram into it and cause it to collapse. There are a lot of ideas for what can ultimately make these things collapse. That's an active area of research. Go ahead. Oh, you're just stretching? I should say, if you need me to stop at any point, okay, then you just raise your hand and ask.
So when you say equilibrium, do you mean like pressure equilibrium?
Yes, I mean that it is, at least on a dynamical time scale, it is stationary. It may still be evolving one way or the other over a long period of time. But so, for example, if the sun were not in equilibrium, and we just said, okay, let's take away all pressure support and let it collapse, how long would it take to collapse to a point? It'd be gone in 30 minutes. And that's just the free fall time of the material to collapse. I think to a good approximation, the sun's an equilibrium object. What do you say? Yeah? Okay. All right. Moving on. Good. All right. Now, there's another component. So we don't exactly know what causes them to collapse, but gravity's involved. And so they do collapse at some point. There's some trigger. And when they do collapse, we do know that these objects have some rotation to them. And we go out and we can actually observe disks. So these are proplyds. And a lot of these here are in these teardrop shapes because there's a massive star somewhere over here. And the winds from that star are actually creating the teardrop shape itself. But if you look closely, there are actually disks in those objects. So we actually can see that disks are present. And in fact, we have even better images than this. So this is a disk around a fairly nearby star. This is there's a mask for the star, and it lets us see the disk. And this is a scattered light image, so there's both. This is really fine-grained dust, and if you actually look at the radio emission from this, you can see that there is some gas there as well. But this is actually an old disk. This is fairly evolved. There's probably something going on that's creating this structure. Maybe they're planets, or maybe it's a nearby star. So that's an active area of investigation. This is just the deprojected. So we just took the disk, which happens to be oriented like this, and said, okay, let's just flip it. So it's just stretched accordingly.
So where did you say they come from again?
So this is from the collapse of some of those clouds. And now the clouds themselves are just formed due to all of the turmoil that's in the galaxy itself, and also the gravity of the gas. And so you're going to have then the formation of these clouds and then the dissipation of these clouds. And in the densest regions, you can get a star. And the details are still being filled in, but that's the basic picture. Okay, so we're back here, and this is what we essentially have. So we have some dust and molecular gas. Something happens, and we get collapse. As it collapses, we get this nice object here. We get some protostar, and we get a gaseous disk. Now, based on this idea of a disk, and also what we see in the solar system, there came this idea of this chemical equilibrium condensation gradient in the solar nebula. This is the solar nebula hypothesis. The idea that the solar system was once formed from a disk of gas and dust. And by dust here, I basically mean anything other than hydrogen and helium that's in small little pieces, that isn't in a gas phase. All right, so here's the basic idea. If we have a disk, and we have the protostar here, and we look at the temperature in that disk as we go away from the star, it gets colder as we go away from the star. Okay, that's all you need to know at the moment for understanding the rest of this diagram. So it gets colder as you go away from the star. There's going to be a point at which it gets cold enough for water ice to actually condense out of a vapor form and go on to whatever solids are present. And so interior to this ice or snow line, you can have rocky things. It's too hot for it to snow. On this side, it's cold enough for ice to be stable on these solids. And so what we have is then this region where we can get things that are more like asteroids, and over here things that are more like comets. Now, why is this a big deal? Well, people are arguing about that, but let me give why it was brought up. Let me give it. So first of all, if we look at composition by mass, 98% is hydrogen and helium, and you only have 2% of what astronomers call nets. Anything other than hydrogen and helium is a metal in astronomy. Okay, of the metals, we have condensed solids. 0.5% we would call rocks. 1.5% are ices. Now this contains things like methane, as well as water ice. But so it's just astrophysical ice. But a lot of it is water. About 1% of it or so. So what happens at some point is you have a factor of 3 more material to build things. So that may actually play a role in the way things form. This is just a quick breakdown of some of the different elements, and now this is by abundance, not by mass, that was believed to occur in the solar nebula. Now, this is taken from the current abundance of the sun, and we just assume that the sun's abundance today is representative of the abundance in the solar nebula when everything formed, which is going to be okay-ish. Some things here to just kind of think about. It's a little bit fun. You have all the mass is going to be dominated by hydrogen and helium, but we look at ourselves, and by mass we're mostly oxygen. You're standing on mostly oxygen, but the sun is mostly hydrogen and helium. So I guess it depends on what you're saying by mass or by number. But by mass, definitely mostly oxygen. By number, I think mostly hydrogen. So our biased view. So if we look out and we say, aha, so it just happened to be hot in the inner part of the nebula. It was hot in the inner part of the nebula. We didn't get ices. There wasn't a lot of material. It wasn't very cold. And so we're only going to get these rocky things. Then as you go farther out, you have actually ice that can actually help grow very large objects. And maybe those large objects become so big that they can hold on to a lot of gas. And maybe that's why we see these solids here and then we see gas giants as you go far enough out. I mean, this right here, somewhere around here it is the ice line. That's where the ice line would have been. So, yeah, that all kind of hangs together, more or less. What can go wrong? Well, let's talk a little bit about planet formation theory. So I already kind of had one miracle I introduced, and that was in the star formation. Where I said we have some type of object, and we have we need to get collapse, and we don't exactly know how collapse happens, but collapse happens. All right, so fine, working out those details. And now here comes something that's interesting. So how do you go from dust to a planet? So if you're in a disk of gas and dust, that dust starts off at 1 micron, a millionth of a meter. And you need to go then, at least for the Earth, to something that has a radius of 6,000 kilometers, plus some change. If you want to go to something that might be the core of one of these gas giants, you have to go more. So we have orders and orders of magnitude to overcome. This is one of the first stages. So go on, you look at a window, where you see some sun, you see all the dust floating around. So in the solar nebula, you have maybe a little bit of turbulence of the gas moving around, and you have some Brownian motion. You just have these solids that are moving around, and occasionally they run into each other and stick. Okay, so they start sticking, and eventually you get lots and lots of dust bunnies. And since there's no one to sweep, they start sweeping themselves, and they grow. Okay, so this is the basic idea. So we start with something very small, they start sticking together, things are nice and gentle, and they grow. What can happen? All right. Well, if you look here at this very rough sketch, I wrote, okay, so we have rotational sport and gravity this way. So the gas is in orbit. That's true. But there's one little tiny thing. There's also, this is also a gaseous disk. So there's some pressure. There's a pressure gradient that goes out. It's a very small pressure gradient compared with the rotation, but it's there. That means the gas doesn't have to orbit as quickly. If it's gas, it doesn't need to orbit as quickly as what the solid needs to orbit. So if you have your dust bunny needs to go fast to stay in its location, and the gas needs to go just a little bit less fast. That means the dust sees a headwind. And so as you start forming these dust bunnies, at first the dust bunnies are completely stuck with the gas, because they're so small. So drag works really well. So same idea, you see the dust just floating around in the gas, in air, when you look through the window. It's the same idea. Once they're small, it doesn't matter. Once you start getting into rocks, they fall. So once you start getting to rocks, they need to fall at the orbital rate in order to stay at their location. But when they start doing that, there's gas in front of them that's going a little bit more slowly. And that creates a headwind. That means that it actually causes the dust to move in, as long as that pressure gradient is outward. So here are the aerodynamics of solids in the solar system. This is a seminal paper from 1977 pointing out the concept of the meter barrier. The idea is actually quite simple. You are slowly building up rocks, they're coming together, you're making some pebbles, all right? But as you make them bigger, then the time scale, this characteristic lifetime, the time for them to go from their location and fall into the sun, just from gas drag, is given here. This is in years. Once you hit 100 centimeters, once you hit 1 meter, the lifetime for a boulder to fall into the sun from drag is about 100 years. Now, I haven't gone into this yet, but the time scale to form a planet is measured in millions of years. That's a problem. Because as soon as you form something big enough to start moving on to building planets, on your way of going from these 1/1,000,000th of a meter up to thousands of kilometers, you start losing that material into the sun. Okay, well, we haven't considered all possibilities, certainly not. So what's one thing that you could do? Well, maybe there's a lot of turbulence in this disk. Yes, the disk is turbulent. It's churning. It's like convection in the atmosphere. There's stuff just moving around, and there's a lot of motions, and that moves all of the solids around. Okay, yes, if we do that enough, we can keep that march. We can slow that march down. Okay, there's another problem. I'll give you move things around, and it's just churning around, and they slam into each other, and they grow. So this is by Verm and Bloom. These are some very interesting fellows, and their lab consists of ramming things together and seeing if it sticks. So this is a diagram of ramming things together and seeing if it sticks. They actually have this one experiment, the Wilhelm Tell. It's a crossbow that launches a cake of dust at another cake of dust. And they do these things and see if it sticks. And they do it in drop towers and see if it sticks when things are in free fall, and they do that. It's very interesting stuff. Okay. So if you have a small thing and it collides with a small thing, it sticks. A smaller thing, a slightly larger thing, a slightly larger thing, it sticks. And you keep doing this. But once you get to the size scale in which you are making meter-size objects, you first go into a regime where there's mass conservation. Two things collide, they bounce off each other, and they may have traded mass, but they end up having roughly the same mass. You try to go beyond a meter, and you're just going to be destroying objects. You're hitting them together too quickly. In order to get the turbulence that's needed to keep the things from moving in due to aerodynamic drag, they're going to be ramming together too quickly to grow. So the meter barrier is still there. You don't get around it. Now, there are a couple ideas that are put out to try how to actually get around this, and some of them involve instability, such as the self-gravity of a group of these solids becomes so large that all pebbles collapse and form a giant kilometer-sized thing in one go. And that's an area that people are really looking hard to try to understand. Another idea is maybe there's a pressure bump. Instead of always having this slowly decreasing pressure as you go out, maybe there's a wee bit of a bump. And that wee bit of a bump matters because now you have gas that's moving slower than orbit on one side of the bump and faster than a normal orbit on the inside of the bump. So on one side you have a headwind, and on the other side you have a tailwind. So it marshals you right into that pressure bump. Maybe you can form things there. Maybe. But these are ideas that are being explored. But let's just carry on. There's still a lot more work to do. And we're only a wee bit into this 4-hour lecture. So if you can get planetesimals in the first place, where you go onto planetesimals here, I mean things that are around kilometer-sized objects or so. If you can actually get there and you form something that's of that size, then it's not so much of a problem at this point anymore to form a large object. So there are a lot of details that are getting worked out, but the overall picture doesn't have major complications. You have these kilometer-sized objects, they slam together, some of them grow, and some of them get a wee bit bigger. The ones that get a wee bit bigger start to capture more material because they are bigger. Then eventually they get so big that the gravity matters. And gravity actually makes them look bigger. And so it focuses, it's called gravitational focusing. What it does, it's able to actually capture material. When they're very small, the gravity doesn't matter so much until they actually hit. But once they get big enough, then you actually are able to bring in material, and you're bigger than you look. And so you grow even faster. And that's the point at which you get into runaway growth, where now you have a few things that very quickly dominate the material around. And this is how you can go from a whole bunch of planetesimals to having a few very large objects, which maybe we call terrestrial planets today. This is a simulation that just shows that basic idea. Here are some embryos, and I actually had to cut this off because it was a very long figure. But it started out with just a bunch of very small embryos. They collided, you get a few winners, and those winners keep growing, they combine to make something really big, and as you move through, you quickly are eating up the material or scattering it away, and you end up with then just a few large things. So this is the idea of runaway growth and how you can go from these planetesimals to other objects in relatively short period of time. All right, so now we have these terrestrial-like objects. These are just rocks that are forming together. We have the icy objects. We have the ice that's able to form. And now, once these objects get so big from the oligarchic growth, you eventually reach the regime in which they're able to hold on to gas. And if they hold on enough gas, then that gas actually has enough mass to change the way the rest of the nebula sees that planet. And so you add a little bit more mass, so it's more massive, so it can hold on to more mass. Because it's more massive, it can hold on to more mass. Because it's more massive, it can hold on to more mass. It's a runoff. But the clock is ultimately ticking. So if it were just solids, then we could just wait around for our cosmic dust to all be swept up by a few of these oligarchs. But time is actually ticking. And if you go out and you measure disks, the effect that disks have on their stars, we're actually measuring then signatures of accretion of a disk onto a star. Okay, certain lines, certain transitions are signatures of accretion. If you look at that, you have about 2.5 million years on average for gas to last in your disk. So you need to go from something that's a millionth of a meter to something that's big enough to start holding on to lots of gas in less than 2.5 million years. And that is our timeline for planet formation. Yes, there are some that go out to 10 million years, but half of them are gone in about 2.5 million years. So that's our timeline for planet formation. Yes?
So you're saying that the stuff that's out there to make planets is being sucked into the star in 2.5 million years?
So what's happening with that is you have to, because the gas is happily in orbit with a little bit of a pressure gradient, in order to actually get it to go into the star, it has to lose angular momentum. And so there needs to be an accretion process itself in which some of the momentum is given to material farther out in the disk, and that allows some of the material closer in to move in. And so you have this accretion process, which is this transfer of angular momentum from the inner regions to the outer regions, and that's what allows it to move in. And so you have this period in which we see that material is falling onto the star. And it's due to this accretion process ultimately. After 2.5 million years, that accretion process stops. It doesn't mean that gas isn't present, but it's either low enough that it's not accreting in significant quantities, or it's starting to be removed. And there are a couple of different ideas for how you can remove gas, but a lot of them involve energetic radiation and the gas becoming thin enough that you can just heat it all up and photoevaporate. Yes?
This 2.5 million year time period you're talking about, what's at time zero? Is that when the star
Yeah.
turns on?
So actually, most of, for the sun, once it collapses down to the protostar, you have something like 10 million years for it to actually become a star. So it's quite possible that you had most of planet formation done before the sun became a hydrogen-burning star. So it was just slowly contracting and heating up as it did. For the sun is slowly, or any type of star is slowly evolving and gaining mass. And as it goes on, it's gaining less and less mass as it moves on. But the sun itself was still for these stars here, they're still in their birth phase, where they're still contracting. They haven't started burning hydrogen. So could you say your question one more time, because I'm not sure if I answered it.
Well, I was wondering, what was at the beginning of the 2.5 million year
The t equals
time
0.
period?
So the t equals 0, sorry, I got off on a little rant, so I couldn't quite do it. So the t equals 0 is where there are two ways to define t equals 0. One is the oldest solids that we know of. And the oldest solids that we know of are CAIs. These are calcium aluminum rich inclusions. And they form 4.568 million years, 4.568 billion years. Those usually set t equals 0 for planet formation, but we don't know when that t equals 0 is for the actual formation of the disk itself. But those things are so old that we can kind of take them as more or less the formation time of the disk, because the collapse time for this material is about 10 to the 4 to 10 to the 5 years. And the whole system is evolving over millions of years. So we don't know exactly where to pinpoint t equals 0, but the collapse time roughly sets it. And there's some give or take of 1/10 of a million years. But so we roughly think of t equals 0 is when it collapsed.
And is that to do with the sun?
That's the gaseous cloud from which the sun was born, and the core that's in the molecular cloud. So to try to understand the timescales that are involved and gas giant planet formation, there are actually two hypotheses that are put out, and they're often described as competing. I don't actually think they're competing. I've done a little bit of work with this one, and I do think that this one that's called core accretion plus gas capture is the best way to explain most of the planets that we see, but this one probably is going to form some planets. It's just a matter of understanding how frequent one pathway is over another. In this particular one, this is the theme that I have been discussing throughout this, where you have then this rapid core growth. So these lines here, these first ones are very rapid growth of a large core. So this is a planet at this point. It's a planet. It's very large, it's very massive. But at this point, it actually no longer has solids to accrete. It's actually accreted all the material that's near it. And so it can't accrete anymore, and so it kind of stalls. And it very slowly is able to get more material as things get kicked around during the planet formation process. And it actually captures a little bit of gas. But then, what happens? As it's capturing, this is the solids, this is the gas here. Eventually, it's able to hold on to so much gas that roughly the gas is about the same mass of the solid core itself. Once you reach that rough transition, you can very rapidly capture gas. You get a runway. This is where you become a little bit more massive, so you can hold on to more gas. So you become more massive, and you can hold on to more gas. And you just run away. this is, for this one, disk instability, this is where the gas, the mass in the disk becomes so, actually begins to dominate locally the dynamics of the system. The disk is so massive that the self-gravity of the disk itself matters. And when that happens, you can actually get the disk to break up into little pieces. And this may actually be a source for other stars, for multiplicity, and maybe a source for brown dwarfs, something in between a planet and a star. Or it may form some of the very massive planets. Let me give you a picture of this. You're looking face down onto a disk. This is a supercomputer simulation. Self-gravity has caused the disk to break up into spiral arms, and some of those spiral arms themselves break up into clumps. And these clumps are then several to 10 Jupiter masses. And they'll grow. Now that may seem like a lot, put in comparison with Jupiter, but we do know of planets that are 10 Jupiter masses. They exist, so that's not so odd. I'm going to go ahead and skip over that. These planets here probably did form from core accretion, although that's actively being researched. So here what happened is we had a transition in which we were able to form very large cores that got so massive that they were able to capture gas. Jupiter was able to capture a lot of gas. Saturn was able to capture a little bit of gas. And these two planets were so far out that they weren't able to get big enough, fast enough to capture gas. This is a basic idea. So everything should be like ours, right? And that's we have this great data, we have this nice story that hangs together. What can go wrong? So you go out and you take a look at other stars, and you hope you can find planets. And actually, one of the first planets, although it wasn't appreciated to be a planet at the time, was discovered by one of the profs at UBC. But it wasn't appreciated to be a planet at the time, so this isn't giving credit as being the first planet that was discovered. Right here, what happened then in 92 and 93 is that they found planets around pulsars. These are the remains of a very massive star. And they found they found rocky planets, or let's just say low mass planets, around this dead star. All right. So that's weird. It's a dead star. What's a planet doing there? Let's ignore that. We'll just ignore it. It's something weird. It's going to be a small effect. We can worry about it later. Well, something happened in 1995, and that is a Jupiter mass companion was actually found around a solar-type star. Now, this blew everyone away for multiple reasons. One, it was a planet around a solar-type star, somewhere other than the sun. The second thing, so Jupiter orbits the sun in 12 years or so. This orbits its star in 4 days, more or less. So that's a little different than anything we have in the solar system. And you can say, oh, well, you know, that's some freaky thing. But then they just kept coming, and then people were really interested, so a lot of money got dumped into these planet searches, and then a lot of people went into it, and now we just see this huge growth in the number of planets that are known. Now, it turns out that these objects that are like, there's 51 Peg here. Now, these are actually going to, it turns out now they're low percentage objects. These things are still weird. They're out there. They're not very common, but they're common enough for us to have to worry about them. These are about 1% of them or so. But as we kept looking at different systems and kept improving our techniques, we now know of somewhere around 1,000 planets that have been confirmed, and we have thousands of more that are on the waiting list. These are planet candidates in which we expect most of them to be actual planets. This is from the Kepler Transit Survey. It was just looking for planets to pass in front of their star and to dim the light. And we see these are orbital period in days. And this is a radius relative to Earth. We see a very high abundance of super Earths and mini Neptunes. There are thousands of planets that are now known, and if you run the numbers, you have well over 30% of stars having planets.
So where are they all located?
So these are in the just around the sun. Some of these are what is it? A few thousand light years or so in one particular field, but it's a whole bunch of distances. But it's all within the local area in terms of local being defined by the galaxy.
That's what you said, 30%?
It's over 30%, yes. Over 30%. And it's even more interesting than that. And in fact, 20% of stars have multiple planet systems within about 0.5 AU. So let me put some more perspective on this. Here are some cartoons, NASA-fied, that show some very interesting systems. This one is Kepler 11. So that's a true comparison in terms of its size, because Kepler 11, the star, is about 0.95 times the mass of the sun. So it's just a little bit less massive than the sun, but you have to take the square root, so who cares? It's for all intents and purposes, this is a fair comparison. There are 6 planets in this system that are within the orbit of Venus. 6. And it's not a little dinky thing. These are super Earths, and these are mini Neptunes. This is completely different from what we have. And it's not the only system either. This is also around the G star here. This is Kepler 20a, where we have some other planets that are inside the orbit of Mercury. Then you have this Kepler 22 system, which is a super Earth in the habitable zone. And then we could just go on here. I could go through and we could do stamp collecting and say there are lots of planets, but ultimately that's the point. There are lots of planets, and they're actually very close to their star. Yes?
Well, are you saying they're within the Milky Way system?
Oh yes, yeah, they're all in the Milky Way.
They all are?
Yes. There is the idea of looking for extragalactic planets, and you have to do that at the moment through something called microlensing. But everything that I'm showing here are in the galaxy.
Do you think that there are more planets than outside of that radius, but we just don't see them because their period is longer?
Well, oh yes. So we've constrained. So this is a very important point that within about 0.5 U already we have 20% of stars having multiple planets, and that number only goes up because we've only constrained to 0.5 AU. Once you go farther out, right, you're going to pick up more. But we can't really say for any certainty. We haven't measured that. This is what we've measured. So, but we can strongly suspect.
So that's really turned planetary formation theory on its ear.
So there,
especially that diagram I'm looking at on the bottom left.
yes.
The variation in the sort of the nature of the planets.
So there it is. The question in planetary science and planet formation theory, at the moment, I shouldn't say planetary science, but certainly planet formation theory, is when we look out and we see all these short period planets, these planets that are very close to their star, did they move there or did they form there? How wrong is our theory, or what is our theory missing? That's the question. So there are a couple ways you could do it. And I'm running out of time in my not actually 4-hour talk, so. So there are a couple ways you can move a planet. So let's say everything I told you before is right, but I've missed one detail. And that one detail is, after they've formed, they can move. Well, it turns out, don't worry about this messy equation, but this is from a paper from 1980, in which they were looking at rings. And in here, they were doing these calculations for how things should move around in rings. And they said, you know what? The ring system's kind of like the environment that you're forming planets. And in fact, thus, Jupiter's semi-major axis will evolve on a timescale of blah. So actually in 1980 they predicted that in fact planets should move. But you know, that was kind of weird. It didn't really fit our story that we were talking before, so it wasn't really tested until recently. And then this theory actually was right. Or this hypothesis derived from the theory of planet migration. There are a couple ways you can move things. You can move things with gas, you can move things with planetesimals, and you can move things with other planets. Let's talk about those in turn, and I'll just do this briefly. One, don't worry about this right here, that's a detail. But here, what you're seeing is the radius. And now what I'm taking is the azimuth, and I'm stretching that azimuth out and turning it into a square. So this is radius and this is azimuth. And one,
Radius of orbit.
this is in the disk, radius in the disk. And this is where I'm going to stick a planet in a gaseous disk. It looks weird here, stretched, because of just the ratio of the azimuth and the radius. Okay? So this is more or less a sphere here, and then it still has these spiral arms. So what happens when you put the planet in the gaseous disk, then the planet is going to perturb the disk. But in turn, that perturbed disk can perturb the planet. And it's those interactions that can actually make a low-mass planet move around. And so we are screaming at each other about which way the planet moves. We don't know. It depends on a lot of messy details. But you can actually make the planet move. Just do this. But this is for something that's more like Earth. This wouldn't work for something like Jupiter. To make something work for something like Jupiter, you have to go and do something called another type of gas migration. And this is where the object becomes so massive, you're looking at a projection of the gas. And this is a planet that was just artificially placed in a gaseous disk, and we're saying what happens to the gas. The planet is so massive that it actually clears out material and forms a gap. And then what happens is the planet becomes locked to the disk. And however then the disk evolves, whether it's through accretion, if this gas is moving inward through accretion processes, then it will move the planet along with it. And so you can move a planet in that way. And this is kind of neat because you can move a planet very slowly, keep it nice and circular, and bring it close to something else, maybe another planet, for example. So you can then ask, well, okay, what happens when the gas goes away? That's when you lock the planets into place, when the gas goes away. Well, not really. You see, you still have a lot of these leftovers from the planet formation. We call them asteroids and comets today, but when they were forming, they were planetesimals. And although you have a planet which is very massive, and then you have a lot of low-mass objects, you have many of the low-mass objects. And that can actually cause the planet to move. If you kick them around, if you just eject the material one way or the other, you can actually cause the planet to move. Is there any evidence that something like that happened in the solar system? Yes. Pluto. And objects like it, the Plutinos. You can actually, the Plutinos are in this 2 to 3 resonance with Neptune. Every time Neptune goes around 3 times, the Plutinos go around twice. The way you can lock those objects into resonance is if you very slowly move the planet out. And one way to do that is through the accretion, or through interactions with planetesimals. And I'm going to go ahead and show you one more type of way of moving a planet. And that is, why use planetesimals when you could use planets themselves? So imagine that you form 2 planets close to each other. And while the gas is present, they actually keep their orbits fairly circular. It stabilizes the system when you have gas present. Then you take away the gas. You no longer have this buffer that can stabilize the system. And what can happen is you can have the planets interact gravitationally. And through those interactions, they can actually become orbit crossing. And you can have planets that throw out other planets, and as a result, change the orbits of other ones. And if it changes the orbit so much, you can actually bring it very close to the star. And then through gravitational interactions, through tides, you can actually dissipate the orbital energy and make it more circular. Then one last thing I want to leave you with is kind of a story of where the solar system sits in terms of the way things have migrated. And I don't want to give you the impression that everyone thinks that this is right. I'm just trying to give you an illustrative idea of how planet formation theory has changed and directions that people are currently exploring. Let me be very clear. This is an idea for exploration. We have a couple puzzles. We have the Plutinos. We have to explain the Plutinos. We have to explain the low mass of Mars. Didn't really have time to talk about this, but Mars having a low mass is actually peculiar. You can ask me about it afterwards. I'm running way too late. And there's something called the late heavy bombardment, just how you obliterate things later on. The thing to take away is that in order to explain multiple things that we see in the present-day solar system, one idea is that you form the planets in a much different location than they are today. Jupiter, through some of these disk migration things that I only very briefly touched on, moved inward. Moved inward to about 1.5 AU. Saturn later caught up, and they went into a resonance. Then, through their mutual resonance and interactions with the disk, they moved out again. And they actually caught up then with Neptune and Uranus, and yes, I said that in the correct order. One of the ideas here is that those planets switched. And then you actually have a setup for a later stage that I'm going to go into. The whole idea here is that you have this truncation of the terrestrial planets in this inner region because Jupiter and Saturn moved very early on, and they rearranged the mass. That's the point to take away. And I'm not trying to say that that is indeed what happened. We don't know. This is a direction that some people are exploring, and people are taking it very seriously. And then after you've set this stage up, you have then Jupiter, Saturn, Neptune, Uranus, and then through planetesimal scattering, you eventually put the whole system into an unstable state. You scatter the planets, drastically change their orbital configuration, and in fact you can even switch the order of Uranus and Neptune to make the present day configuration more or less. So what's happening, planetesimals are getting kicked in and they're moving these planets as a result, and then at some point they reach a threshold where Jupiter and Saturn hit a resonance and interact very strongly gravitationally. This is showing their average orbit. And boom, it scatters all these planetesimals. You rearrange the solar system, and you then slowly move Neptune outward to form the Plutinos. Again, I'm not trying to say this is what happened, this is more of a story, but it gives us some ways to actually go out and test some of the things we see in the solar system and see if it matches. And there's some things that this works for and some things it doesn't. The thing that I want you to take away is exoplanets have drastically changed the way you view the solar system. We know that planets migrate. There's no reason why the planets that we have in the solar system also did not migrate. They could have formed in very different places. So we're still exploring options for the solar systems. There are a lot of fantastic ideas, but we're still not sure what's going on. How many of you have seen this image? How many of you haven't seen this image? Okay. This, we started with Voyager, we're going to end with Voyager. Voyager is it's a distant probe that we've launched as a species. This was taken at 40 AU, and this is an image of Earth. Can you see it? That's Earth. It's Earth suspended in the sunbeam. Our entire civilization is there. Everyone you ever knew, everyone you will know, anyone who ever was, lived on this speck of dust. And we're just a speck of dust looking for other specks of dust. That's where I'll end it.
So when we look out and we see a bunch of star formation out there
Yes.
at different stages of formation.
Yes.
We see, let's say, a dust cloud. Yes. Now, is there a difference in composition between one dust cloud and another? And could that explain the different types of solar systems that result? Could there be different percentages of metals, as you say?
There is a known correlation between the metals in a star and whether it has planets. So there is some known correlation between those. So metals matter. So more dust helps planet formation. In what way is still being investigated. Some people are screaming this is definitely then telling you that you have the core accretion, you have dust bunnies colliding together, eventually forming something else. But it may be more complicated than that. But there is definitely a correlation with that. And that's actually...
So in the solar system, you're saying at this time the composition is 1/2 of 1%, as you call them, metals, other than helium?
Well, it's 1/2 of 1% for rocks, for silica. So for anything that would go into forming a rock. So we're looking at silica,
Oxygen.
carbon, oxygen. Mainly oxygen, then carbon. So and iron. So those are the things that are going into forming the rocks. The 1.5% then, that's all going to be ice. That's all.
When you were talking about the Jupiter and Saturn resonating and sort of throwing it, are you talking about within like this accretion, this era,
Yes.
2.5 million? So this is very early on.
That's right.
This migration.
And there, I went way over time. I'm sorry, but I would like to tell you about chondrals, for example, and what they tell us. And these are components of the meteorites, and they allow us to then date things. And so we can then date things relative to other objects, and we can say when does one type of meteorite parent body, it's an asteroid, when did that form relative to some other asteroid? At least for the little piece of it that we have. And when you do that, you start to get a picture of how long things took to form. It actually turns out that we have ground truth for another planet, and that's Mars. And that's because something a while ago slammed into Mars, knocked a piece of rock from Mars into orbit, and that rock fell to Earth as a meteorite. And so we can actually go and we can collect those type of meteorites, and we can analyze Mars, for example, Mars's crust. And from that we can get an idea of when Mars's core formed, because actually the crust then is depleted in certain elements, which would be best explained by it actually differentiating, where you have something that's molten and you have the lighter material forming the low density rocks which float, and you have the metals then which then go to the center of the object. Differentiation. So meteorites can tell us that, and they can also then, from different age constraints, they can let us know that Mars was probably half formed at about 2 million years. So we actually have significant formation of planets in the presence of gas. So a lot of these ideas of how you can move a planet around probably are quite relevant. Yes.
What's problematic about massive Mars?
Yes. Okay, so the issue is, this is a model that works. If you start with just a whole bunch of embryos, I don't actually have one that doesn't work, but if you have a whole bunch of embryos and a bunch of planetesimals, and you just make a disk that goes out to, say, the asteroid belt, and you just say, okay, I'm going to form planets. and you just let things bang around, you always end up with a very massive Mars. It's extremely hard to get a planet with as low of a mass as Mars in Mars's location if you have a reasonable distribution of solids that continue to go out to the current asteroid belt. So, well, one thing that does work is if you had a truncated ring of material, of solids that only, of embryos and solids that only went out to 1 AU, current Earth location. And then you allowed everything to bang together, form stuff. You could then eject some embryos, and one of those ejected embryos can be consistent with the mass of Mars. And so it looks like Mars is a stranded embryo. And so in order to do that, though, you have to deplete the mass. And so that's why these ideas of moving Jupiter and Saturn around and then moving them back and shuffling, they do the hokey pokey and they're somewhere else. That's why people are looking, exploring these routes. It's because you have to get rid of that mass in order to form something like Mars. So there are all these puzzles that seem, it's like, well, Mars is there. What's so problematic about that? One way that I'm exploring goes back to the closer to the beginning of the talk. Sorry, I'm doing the annoying thing of flipping through all the slides instead of just exiting and going to it. There we go. Maybe we don't have to worry so much, at least initially, about all the solids drifting in. Maybe that's exactly what they did. Maybe they all just drifted in. And they had to have been stopped at an inner location for sure. I don't know what would do that, but maybe they did, and maybe that's what depleted the asteroid belt. And maybe that would give you the setup to form something like Mars. You still have to figure out a way to stop it. So no matter what, we're invoking miracles here and there. But it's just, which one do you prefer? Which one's less offensive?
What about the moon?
So the moon probably formed from a giant impact. So this is after the leftovers of, we have all these embryos that are going around, and some of them are probably the mass of Mars, and they're getting kicked around between terrestrial planets, and then occasionally one's going to slam into a terrestrial planet, and we were one of the lucky winners. And so what probably happened is the Earth was grazed by a Mars-sized embryo, knocked off the early crust of the Earth, and that was able to reform as the reason why there are a couple lines of evidence for that. One, the bulk composition of the moon matches very well to the composition of the Earth's lithosphere, the outer crust of the Earth, of the planet itself. And it's very hard to make any other theory work.
So if the Earth had not undergone that collision, the composition of the Earth today would be quite different. There would be a lot more. Would there be a lot more rocky crust, or
Well,
in relation to the iron core, I suppose that you could have more.
well, it's going to affect it, but the moon is still only a percent or so. But still, it's a percent of that outer layer, so we can kind of go back and forth. But it's going to affect both of the systems, but we still have then the composition that's left over. It's the composition that we're ultimately matching. So you could take some of that material, but still you're taking some of that mass and putting it out there, but it's going to be the same stuff.
When people make observations of the extraterrestrial, extrasolar planets, you need a number of orbits of the planet. Correct. Before your commences there. And so the ones a long way out, you haven't been able to see them.
That's correct.
Already.
That's correct.
So the observations now are highly oriented towards the small orbit planets.
That's absolutely correct.
Right. So presumably, as the years go by, we're going to observe more distant planets in these same solar systems.
That is definitely something people are pursuing, and that is the expectation, that some of these systems are going to have something farther out. And we just haven't been able to discover it yet.
Which would be very useful in all of these theories of formation.
That's right, that's right. One thing that I'm particularly exploring is whether you can turn one of these tightly packed interplanetary systems into a solar system if we have outer gas giants. There are some ways to do that with dynamics. One quick point along those lines, this is how long we've really been observing, and remember Jupiter's orbit is about 12 years. So, you want at least one orbit. Go ahead.
Of all the extrasolar planets, are they going to find moons around them?
So the expectation is that there should be some moons. Eventually we'll be discovering moons, since it's hard to actually do that at the moment. And people are looking though, and they've put limits on the detection of moons. And they've been able to say that there aren't many of any like Earth-like size around some of these Jupiter-like planets, so Neptune's within the sample, but there could be smaller. We just don't have the sensitivity.
Presumably you need at least 2 orbits, just one could be a hiccup.
You want to, so, and actually this one here, you didn't even have an orbit with that one. And then so it was that's why it wasn't immediately just thrown out, said, yes, this has to be a planet. And so they're very cautious about it, rightfully so. But you do want more, certainly you want more than a planet, more than an orbit. You want to do a lot better than that.
One or two more questions?
The orbit swapping, now is the orbit swapping you're talking about with the gas giants, is that something that occurs within that first kind of 2.5 million year formation phase, or is it something that occurs later? And if it occurs later, of the age of the 20% you're looking at the short orbit planets, are any of those at a stage where they might be in migration to,
So this stage here is in the presence of gas. And so this would be within the few million years of where you're moving Jupiter and Saturn. This stage can take place well after the gas is dissipated. Because now this is just scattering planetesimals that ultimately lead the planets themselves to interact. And so this can take place over tens of millions of years.
and the model that you had where you had 3 planets and one was forced into a circular, a short-term circular orbit and a medium-range elliptic orbit, and then there was one that was forced out of the picture. Now, was that in the gas phase, or is that like
That would be a late stage evolution.
late stage?
That's a late stage evolution. So some of the systems that we see today could be dynamically interacting would eventually fall apart, at least for the system that as we see it today. But when a lot of the models for these systems are integrated far into the future, and you could also make the argument, well, is it likely that we would catch a system that's on the verge of instability? And then you could kind of start to rule out. So most of the systems that we're seeing are probably stable for a long period of time, but they should probably be, some of them will eventually, after you wait long enough, go unstable.
And if there's a large body out towards the Oort cloud or something like that, that lends evidence to your model that you're speculating on, right? Because I think I read that there was a paper about something about gravitational evidence for outer orbit or whatever.
So that's actually the people have been really interested in whether there's a planet X in the solar system, and a lot of these ideas of how you can kick a planet around would lend to that, to say that's not crazy. So there are a couple different constraints that we have. So recently there was a all sky survey that was able to rule out something like a Saturn mass out to thousands of AU. And it just, we would have seen a Saturn-like object with this all sky survey. The sensitivity was good enough. And we didn't see one. But there could be a super Earth or something that we haven't detected. pulsar timing also constrains it, but doesn't constrain down to the super Earth regime. So there might be something out there. Can't really say at this time. People are looking to constrain it more. That's all we can do at this time, can put stronger and stronger constraints to test whether there's something out there. But yeah, at the moment we're moving on like there isn't anything out there, but people should check. No, I'm serious about that. And we do know that about, well, so there are these, a different type of survey called microlensing, where you wait for the planet to actually create a brightening of the star. And from looking at, from these surveys of microlensing, there are reports that in some clusters, star clusters, that there are about 2 free-floating planets for every star. Now, I don't know, they used a sample of 6 to make that claim. So your mileage may vary, but the thing to take away from it is it's not crazy to suspect that there's a lot of free-floating planets.
Tell by the number of questions, we're going to have to pay you back for part 2 of your 4-hour talk. So I'd like to